Okay, and we're going. All right, so we're doing, our lesson today is going to be on matter, but we're doing a bit of review, so let's go over our bell ringer together. So the first question says, what is the atomic number for iron? Who can tell me what the atomic number for iron is? 26? How'd you figure that out, Story? Right? You go to iron on the periodic table, it says Fe, and right at the very top of the square, you're going to see a big, solid number. And for iron, it's number 26. What does the atomic number tell you? Tells you how many something are in the atom. Not neutrons. Not electrons. Protons. It tells you how many protons. Now, it also kind of tells you how many electrons because in every atom on the periodic table, it's balanced, right? It's a neutral atom. That means the positives are always going to match the negatives. Otherwise, it gets imbalanced. So you're kind of right that it's the number of electrons, but I want you to remember that it's the number of protons because that's the correct answer, okay? Number 2, how many neutrons are in silicon? Nobody know? Okay, well, how do we find the number of neutrons? Should be in your notes. The mass minus the protons. Now, can we use the normal mass or do we have to do something to it? Have to round it, okay? So what is the mass of silicon? It is 28.09 on this chart. So let's call it 28.1. What does that round to? Whole number. 28, right? Now, this is our mass, and we're going to subtract what again? The number of protons. How many protons are in silicon? 14. So we subtract the number of protons. What do we get? 14. So how many neutrons? 14. Take the mass, round it, then subtract the proton number, and then you get the number of neutrons. All right. And so next up, and this is the one that you guys haven't seen before. This one I kind of tripping you guys up a little bit. It's good. Keep you on your toes. What is the mass of sodium chloride if it has one sodium atom and one chlorine atom? What do we got to do? Y'all are quiet today. I'll give you a second to think about it. If we have one sodium atom, one chlorine atom, what's going to be the mass of that molecule? 58? You're close. You're close. So, let's do this. First of all, how many atoms do we have? We have 2 atoms. So let's start with sodium, because sodium is a lower number. So what's the mass of sodium? It's 22.99, right? So, hey, Jadeja, do me a favor. Go ahead and sit right here, okay? Just go ahead. Please sit over here, okay? Because you're distracting people. Ma'am, I'm asking you. I just need you to sit over here, okay? So sodium is 22.99, so we're going to go ahead and just round that to 23. It's close enough. It'll work. So 23 for sodium. What about chlorine? Not 36. 35.45. I'll let you do it 35.5. If there is a decimal, at least give me one decimal place, all right? We don't round the mass when we're doing this. The only time we round the mass is when we're trying to find the neutrons. Because you can't have half of a neutron. Jadeja, I'm going to ask you nicely one more time. Ma'am, I just need you to move, okay? So we've got 35.5 for chlorine. We're going to add that together because both of these molecules or atoms are in one molecule. So we have to add them together. We go here, bring the 5 down, the decimal, 8. You should have 58.5. So someone said 58, someone said 59. That's because we did or didn't round, right? You don't round when you're finding the mass of something. Only round when you're finding the neutrons. All right, next up. Number 4 says, how many valence electrons are there in fluorine? Anybody tell me?
9.
It's not 9. 7. How'd you figure that out? Why'd you subtract 2? So what I suggest for you guys to do, always draw these models out. That way you can see. Because sometimes you'll mess yourself up if you're not careful. So how many electrons are going to be in fluorine? It's number 9, so it's going to match, right? So there's 9 electrons. So we're going to start with our nucleus. Then we're going to get our first shell. How many go in that first shell? 2, right? So let's put 1 here and 1 here. So we subtract 2, we have how many left? 7. So we got to go another ring. 1, 2, 3, 4, 5, 6, 7. We don't have any more left, right? How many can fit in that second shell? 8. So we didn't fill it. If we had an extra electron, we could have put it in there, but we don't have it. So we leave it at 7. So there are 7 valence or outer electrons in that atom. All right? Next up, this is an easy one. What is the symbol for copper? Cu. Yes. Cu. Where do you find that information? Well, where at? What's the book showing you? Periodic table. You're going to look right there in the center. It's either 1 or 2 letters, right? I think some of them, yeah, even some of the higher levels actually go up to 3 letters. But most of them are 1 or 2. And it's going to be that symbol right there in the center. Biggest thing you'll see. Okay, does anyone have any questions on finding the number of valence electrons, protons, neutrons? Is it starting to click? A little more practice. We're going to have some of these, probably every bell ringer will do questions similar to this. Make sure you guys have plenty of practice for this, okay? All right. So put those away and let's move on to the next bit. We have learned about atoms. We've learned about the subatomic particles that make up atoms. And we've also learned about the timeline for atomic theory. Who remembers who we started with? It's a Greek philosopher, 440 BC. If you got your notes, get them out. His name starts with a D. He came up with the term atomos. It's not Dalton, it's before Dalton. The very first guy we talked about. See who this is.
Nobody.
Fake announcement. All right, so the first guy we talked about. Democritus. That's the first guy. He came up with the term atomos. You should have written this already. These are already in your notes. Should be. Hey, Freedeja. Thank you, ma'am. This will be on Blackboard. If I took this up for a grade, so you're going to get this done and turn it into me when you get a chance, okay? It'll be on Blackboard. Why? No. No, you got this. Ma'am, the air in the hallway is the same as the air in the classroom. So the first guy we talked about was Democritus. Maya, what can I do for you? So Democritus is the first guy we talked about, the Greek philosopher in 440 BC. He came up with the term atomos. That's what we use to describe the uncuttable atom, the smallest particle in the universe. So we credit Democritus with that term. He's the one who came up with it 2,400 years ago. So who came after Democritus? He was a chemistry teacher. John Dalton, right. Dalton was next. This guy. Now, what did Dalton change from Democritus? How was his atom different? He said you could do something with atoms that Democritus didn't know about. Woo! Tough crowd. So you can combine atoms to make new substances. Like the sodium chloride we talked about in our bell ringer today. Sodium is a metal, but it's a really special metal. If you take sodium and you put it in water, it explodes violently. It's a very dangerous substance. Chlorine is a noxious and poisonous gas. So, one, we've got a metal that explodes in water, and two, we've got a dangerous gas. You combine these together, what is sodium chloride? Do you know? Table salt. You sprinkle this on your food every day. And it's made out of a metal that if it touches water, it explodes, and a noxious gas that can kill you. But if you combine them together, you got a new substance, table salt. It's completely safe. You put it on your food every day. Increase your blood pressure a little bit, but that's about it. Isn't that weird? I always thought that was kind of odd. So that's what Dalton did. He said you can take atoms, you can put them together, and you can make a whole new substance, and it has whole new properties. It's completely different than chlorine gas or sodium metal, which are both dangerous. So that's Dalton. After Dalton, who showed up? He's a guy who did an experiment with the cathode ray. The cathode ray tube, vacuum tube with electrodes, creates the cool light attracted by magnets. This guy had the plum pudding model or the chocolate chip cookie model. Name starts with a T. Thomson. Thomson's our next guy. So Thomson had the plum pudding model, which he thought that the atom was all positive and that it had little itty-bitty negative charges called electrons just stuck randomly in it. That was his model of the atom. So who came after Thomson? Who came after Thomson? He was one of Thomson's students? Rutherford. Exactly. Good job, ma'am. Rutherford. So what did Rutherford discover?
I know we can have our phones down in there.
Put the phone up, ma'am. If I see it one more time, I'm taking it. Put it up. Put it in a pocket. I don't want to see it. It needs to be put up, Jadeja. Put it up. Put it up, ma'am. So what did Rutherford discover? At this point, we know the atom's there. We know that the atoms can combine to make new substances. But now, Thomson told us about the existence of electrons, but Rutherford came in after Thomson and discovered something else. It's the heart of the atom, where all the protons and neutrons are at. The nucleus, exactly. So Rutherford discovers the nucleus. He finds out that it's highly dense and it's positively charged. Y'all remember what experiment he did? Used radioactive material, fired them at a sheet of gold foil. Gold foil experiment. That's that dude. That's Rutherford. He did the gold foil experiment. He wasn't expecting those particles to bounce back, but they did, right? So who can remember who came after Rutherford? This is the guy, we draw his model all the time. I asked you to draw some the other day. Yeah, B-dude. Bohr. Bohr. B-O-H-R. Bohr model, right? What did Bohr discover? What did he figure out? Something special about the way he draws the atom. The shells. That's it, Elijah. Good job. The shells. So Niels Bohr found out that electrons have layers. Right? The higher the layer, the higher the energy. And this is why we draw them this way. It tells us how they react with other atoms. That's why we do it. We still use these models today. You'll draw a lot of these when you take chemistry in a couple years. All right. Then the last guy, it's actually two people. Some crazy German names. Schrödinger and Heisenberg. Heisenberg had the uncertainty principle. You can't know the location and energy of an electron at the same time. And then Schrödinger took that information and came up with the most modern and up-to-date version of the atom we have. That's the cloud model. Y'all remember the funky little shapes, little kind of bowling pin looking thing? You got the center of the atom. And they look kind of like this. You remember that? Try to think of these as 3Ds, like this one's pointing this way and that one's pointing that way. The cloud model says that The electron, I'll wait. Waiting. The cloud model from Schrodinger and Heisenberg says that the electrons don't have a set path that they follow. Not only do they have shells, but they're more than likely in one of these locations, depending on the type of atom, right? Gives you a probability that you'll find it. You're more likely to see the electron in one of these regions than you are anywhere else. And that's the most accurate version we have. So that's our review. We've talked about the atom, all the pieces, and now the people who discovered those pieces. So now what we need to do is we need to take matter, atoms, combine them to make the 4 different states. You guys learned about the 3 states of matter, right? Solid, liquid, gas. Do you know there's actually a lot more than 3? We're going to learn 4, but I've heard there's up to 7 states of matter. We're just going to learn about 4. All right? So I have got some guided notes. This is going to be your assignment for today, but I'm going to give you every one of the answers. All you have to do is follow along and fill in the blanks. Sound like a good job? Easy? Who wants to hand these out?
Me.
Hawa, I saw your hand go up first. So please make sure everybody has a copy of this. Okay. So first thing I need you to do is please put your name on this paper. Okay? Please put your name on the paper. And I have got a nice little PowerPoint for you. This will be on Blackboard, so if you think I'm moving too quick, it will be available to you on the internet. Okay. No, you don't. You're going to be okay. You're going to be just fine. Now, can you guys write with the lights off? Not too dark? This will help you see better. Unfortunately, I don't think... Yeah, you can't really see the presentation too well on the video, but it'll be on Blackboard if you need it, okay? Everybody have a copy? Yes, ma'am. And so will this video. So you'll be able to watch this class on Blackboard. Okay? You need something to write with? You didn't bring a pencil? You in high school didn't bring a pencil with you? You'll have to sharpen it. It doesn't have an eraser. That's what I got.
Give us something to write on.
There you go. You got a table right there, ma'am. Use the table. Okay. So we are starting our lesson. So everybody listen up real close. We are learning about matter. We're going to talk about solids, liquids, and gases, and changes of state. Now, what do I mean by changes of state? Different kinds of matter. Specifically, solids, liquids, and gases. But there's one more you may have heard of, but you don't know much about, I imagine. So we're going to learn about that today. All right, I'll get it to you, or get it from you at the end of class, okay? So if you'll notice, I need your name in the top right, and then below that, each one of these slides has a couple of missing words from it. I want you to follow along and fill them in as we go, okay? They're going to be okay. You most certainly can. If you can't see well enough, you can move up. Okay, so you'll notice right under matter, you've got a spot you can fill in right now, right? Changes of state. Right, there you go. Fill that blank in first. Today is what, the 10th? Yes, ma'am, 10th. Okay, let's do this. Okay, here are the standards we're covering. Our first standard, we're going to investigate the relationship between temperature and kinetic energy. And we're going to also investigate energy changes associated with heats of fusion and vaporization. There are 2 blanks on this slide. That's exactly right. That's exactly right. Let's see here. All right, you got those 2s? Those 2 filled out? Okay, so those are our standards for today. let's move on to a quick review. Make sure you understand some of the key points you have to understand to be able to move forward, right? And make sure I know where you're at before we move forward. Now, elements are substances that can or cannot be broken down into anything simpler. What do you think? Can or cannot? Cannot. I got some sounds put in there, right? Cannot be broken down into anything simpler. So the way I like to think of this is copper all the way down to a single atom. I can have a big block of copper, right? And every one of those atoms are copper all the way down. So an element is a substance that cannot be broken down or made into anything smaller. All right? Now, elements are substances that cannot be what? Broken down into anything simpler. Just follow along. It's word for word. Huh? Just fill in the blank. You missed it already. All right, next up. Atoms are the smallest building blocks of matter, right? Think of them as the Lego blocks of everything you've ever known. Now, elements are made of blank, not the other way around. What are they? Atoms, exactly. There we go. Now the way... Oh, you like that, Chris, huh? Hey, I spent a lot of time making this. This took me a while. So each element is made out of a different type of atom. So think about the periodic table you've got on your desk in your book on page 336, or the one I've got right here. Each of these atoms has a different number of protons. That's what makes them different. All right? Think the atomic number. Now, you guys have learned about molecules and atoms previously? What's a molecule? Molecules are two or more atoms what together? I like to use the term bonded. Bonded. Just like that. So sometimes molecules are made of more than one element, like H2O. What's H2O? Water. Water has hydrogen and oxygen in it. Now you want to know what I think is really weird? Hydrogen is highly flammable. It's dangerous. Right? We filled a blimp, the Hindenburg, full of hydrogen gas. And then static electricity happened. It created a spark. And it blew the blimp up. Right? It exploded. It's very dangerous. Oxygen. Any of y'all ever been to a hospital? Yeah. You ever seen that sign that says oxygen, no open flames? Y'all know why? Oxygen is highly flammable. It's highly reactive. Highly reactive. So it's a dangerous gas. You got to be really careful with it. So both hydrogen and oxygen are flammable. But what would you put on a fire? If you saw a fire at your house, what would you want to do? Put water on it.
I thought you could put salt on the fire.
You can put salt on a fire too. You can smother it with sand, dirt. But most people, when they think fire, they think bucket of water, right? They think water. But the things that make up water are flammable. Isn't that weird? The gas hydrogen is highly flammable. The gas oxygen is highly flammable. But for some reason, when you bond these two atoms together, or three actually, because it's two hydrogens, you get water. And you use water to put out fire. Isn't that weird? So sometimes there are two elements, like water. Sometimes molecules can be two atoms of the same element, like the hydrogen gas that they filled that blimp with. That's H2. So make sure that you understand, molecules are multiple atoms. All right? They don't have to be multiple elements. They can be one element, but it has to be at least two atoms. One atom, then a molecule, and then elements. Elements can be one atom. They can be 1,000 atoms. All right? Atoms make up elements, not the other way around. Okay. Next. So this is where you're going to draw, right at the bottom. I want you to draw a simplified version of these. You don't have to draw this really complex molecule, but I want you to draw an atom, and then I want you to draw a molecule. So if you're confused about what you can draw, just take an atom, connect it to another atom, connect it to an atom, maybe another atom, maybe do an atom here. That's a molecule. I've got a molecule of something called benzene right here. Benzene is a ring of carbons with hydrogens on them. We use this as a solvent in chemistry labs. It's real popular. So this is a molecule of benzene made of multiple atoms. Looks like should be 6 carbons and 2, 4, 6, 8, 10, 12 of those. So 18 atoms in one molecule of benzene. So you can see right there is one atom in that entire molecule, made of multiple atoms. I'll give you guys a second to write that down. If I move too quickly, y'all let me know, okay? I can't help it if you're not paying attention. So you've got a box at the bottom of your page. I want you to draw an atom. Whose model is that?
Right, that's what I'm saying. So what we do next right here?
Oh, I'll get there. We haven't gotten to that point yet. Whose model is that? It's not the newest one.
That's the Big Bang Theory.
It's the Big Bang Theory, Jimmy Neutron. What model? What scientist came up with this model? Nope, not the clouds.
That smart dude?
They're all, I would say they're all pretty smart. This is, yes, it is the guy who did Rutherford. There you go. That's it. All right, so let's move to the next one. Lastly, before we move on to the stuff we're learning today, you have to know what kinetic energy is. And apparently Kendrick knows. What is kinetic energy, Kendrick? The energy of moving objects, right? So if I take this tennis ball and I hold it up, the tennis ball has potential energy. That's energy to do work that's not doing anything yet. If I drop it, gravity pulls down on the tennis ball and work happens. Things move and change. Kinetic energy would be the energy that the ball has when it's moving. Now, what do you think weighs more or has more force? Holding the tennis ball or dropping the tennis ball and catching it? Dropping it. Why?
Say the question again.
Which one is going to press harder on your hand? Holding the tennis ball or catching the tennis ball?
Catching it.
Why?
Because it puts more pressure to it.
More pressure. So this is potential energy, right? It's all the energy of the mass of this object with gravity. Like, I want to pull down. I want to pull down, but you're stopping me. So I have a certain amount of energy that's potential. Now when I let go, gravity starts pulling on the tennis ball. And gravity adds kinetic energy to it as it falls. So the further it falls, it gets more and more kinetic energy because it moves faster and faster. If I drop this from the Empire State Building, it'd probably really hurt somebody if it hit them.
Oh, that's why we have whenever a rock comes from outer space, it be fire and all that stuff.
Yeah, it's got a lot of kinetic energy. Everything you see around you right now, anything you've ever seen, is moving and vibrating. Even this desk is vibrating right now. But it's so small, you can't feel it or see it. It has kinetic energy, and that's where the temperature of the desk comes from.
So right now, everything is moving. We just can't.
Everything. Your glasses, the table, the air around you, everything is spinning and vibrating a little bit. You just can't see it. And that is the kinetic energy of those particles.
Is it moving slow? Is that what we
It's moving in very small spaces. It'll make more sense here in a second. Okay? So you have remember all what are moving? Atoms. There we go. That's your blank. So here are the 4 states of matter. That's what we're going to learn. There's, I've heard up to 7, but we're not going to learn about the other ones. We're just going to learn about the 4. Yeah, plasma.
Isn't plasma blood?
Plasma is a liquid in the blood, but it's we're talking about a completely different kind of plasma. It's kind of confusing. Different plasma. Now, we talked about kinetic energy, and that kinetic energy is the energy of those moving particles. So, as we increase particles' energy, it actually goes through different stages of matter, different states of matter. You're going to hear me say states and phases. Those are pretty much the same, all right? Sort of like your parents ever say, well, you're just going through one of those phases. It's a period of transition. Same thing with changes of state. We're talking about solid, liquid, gas, and plasma. Each of those four are a different state or phase of matter. Now, as we increase the kinetic energy of those particles, we move into higher states. We go from solid to liquid to gas, and then finally to plasma. Right? As you increase the energy, you move into higher levels of matter. Okay? Do we have any blanks there? Should. Just one? Yeah. I'll show you. I'll tell you what to draw. I got you. Okay. So the first thing we're going to talk about are solids. Don't draw this yet. I'm going to tell you what to draw. Now, solids have a definite or constant shape and volume. What do I mean by that? So right here I've got a piece of brass. Okay? This is a solid, right? Pretty solid. Does it have a constant shape? If I leave this alone for a year, is it going to look the same? Yeah. It's constant shape. Does it have a constant volume? Is it going to get bigger or smaller? No. So solids have a solid shape and volume. Now they do that because they're the lowest energy level, and the energy of the bonds in the atoms, right? The links between atoms are so strong that they keep the atoms from moving very far. Which is where people are like, I don't get it. This thing is moving right now? Well, at the atomic level, yes. All those little atoms are spinning and vibrating. But you can't see it because there's trillions and billions of atoms inside this one tiny piece of brass. So if most solids form crystals, but what they actually look like is that. See how the particles are twitching and vibrating? That's the type of movement I'm talking about. No, I got you. I got you. So all of those atoms are moving. This is what I want you to draw. That right there. Now, it doesn't have to be that intricate. Just take about 15 circles, stick them really tightly together, because all of those atoms are bonded together. This is what a salt crystal looks like. You've got two different elements bonded in a lattice. Anyone ever heard the term lattice? Not lettuce. Lattice. A weaved mat. Sometimes you see them on people's porches. They got all the pieces of wood that are crossed. Same thing happens in a crystal. All those atoms line up in a geometric pattern. And we call those crystals. Most solids form crystals. So if we took this brass and zoomed in at the atomic level, you'd see a lattice or crystal formation of all those atoms. And all of these are bound together real tight, which is why they don't change shape. Give you guys a little more time to draw that. It doesn't have to be that detailed. Just make sure you know those atoms are bonded very tightly and they're packed together real tight. Mm-hmm. So you remember this, huh? We ready for the next one? I still see pencils going. Okay, well, I'll move forward then. The next one we're going to talk about is a liquid. Now, liquids have a definite volume, but they don't have a definite shape. What does that mean?
That means they take the shape of whatever is in.
Exactly. Liquids take the shape of their container. If I pour some apple juice into this, it's going to be shaped just like this, right? What if I pour this in there? Is it going to be shaped like this? No, it's a solid. It keeps its shape. But liquids change their shape. Do they change their volume? No. If I have 20 ounces of soda, I got 20 ounces. Doesn't matter what shape it's in. It's always going to be the same volume, right? Now, why is that? Why is it they can flow and they can change shape, but we don't have a difference of volume? Well, it's because of those bonds. In a solid, they're bonded really tight. They're not allowed to move much at all. But in a liquid, those atoms are allowed to flow around, but they still don't want to leave their friend. Like, as long as I can see my friend, I'm happy. But I don't want to go off on my own. That's how those atoms feel. They can move.
They're not stuck together where they flow, but they're separated.
Kind of imagine that when I was a kid, when our parents would take us to like theme parks, some of the parents would have these like elastic cords with Velcro like wrist straps. So they'd strap one into you and they'd strap one into them. And you could move around, but you couldn't get very far. Have y'all ever seen those?
Yeah.
They used to be real popular in like the 80s.
Like a leash for kids.
It's like a leash for kids, exactly. But it's like springy. So you can go a little ways, but you can't get too far from mom. Same thing happens with these atoms. They can move, but they can't move that far. Does that make sense? That's why they can flow, but the volume stays the same. Now this is a low energy level. Solids are lowest, liquids are low. And this is what the atoms look like inside a liquid. They move, they stay close together, but they move in and out. They're allowed to spin and move and flow, but they all want to be close together. And that's what liquids look like. This is what I want you to draw. That right there. So draw a surface, like a waving surface, like you were to draw, most people when they draw the ocean, they do this, right? And then pack some atoms loosely in there. Hey, y'all are doing good today. Super quiet. Did they make you guys run laps last class or something? No? You woke up late? I didn't get enough sleep last night. I was tired this morning. I did not want to get up. But I'm pretty excited about some of the stuff we'll be doing here soon. I've got a lab planned with you guys. I'm going to show you all the changes of state in one lab, all 6 of them. That's going to be fun. I'm looking forward to it. I've already started buying supplies for it. Have we got this? Yeah? So what do you think is the next stage? Gases. All right. So do gases have a definite shape or volume? No. They move around a lot, right? So if I pour gas into a container, is it going to stay in the container? No, it's going to float up the top, right? Most of the time. Carbon dioxide gas would actually stay in here because it's heavier than air. Exactly. So they don't have a definite volume. They don't have a definite or constant shape, and they're high energy, right? Now, what do we call gas moving from a high concentration to a low concentration? Anytime we take a substance in a high concentration and allow it to move out, become thinner into a low concentration, what do we call that? Do y'all remember? Starts with a D. You learned about osmosis, and you also learned about... We're trying diffusion, right? Gases diffuse into their environment. So this is what that looks like. So we take the bottle off of the gas, take the top off, and those gas particles are allowed to filter out or diffuse into the environment. Right? That's what gases do. They have no definite volume because the bonds are so weak between the atoms that they can't hold each other close. They let each other go. Just like, you go do your own thing. So they spread out. This is what I want you to draw. What do you think those arrows represent? The way they move, right? Exactly. Some gas particles. These are high energy level. They spread out or diffuse into their environment. Gases are fun. You'll have a whole section of chemistry. You'll learn about gas laws. Charles and Boyle. Combine, ideal. Learn about some cool French people. Give you guys a little while longer. We about ready? Raise your hand if you need a little more time. Okay. So that's gases. That's the high energy level. What's our last one? Plasma. Does anyone here know anything about plasma? Besides the blood plasma. That's my thing, because I'm a biology person. I love biology. But I also love basic physics. I think some of the stuff you learn in basic physics is just the coolest thing in the world, because it teaches you how biology works. You can't understand how the atoms and molecules and tissues and cells and the organ systems, you can't understand how all that works unless you understand the physics behind it. So plasma is an ionized gas. Now ionized, I'm not going to ask you guys about ions, but I want you to know so you understand what's going on here. All right? Ions are charged particles. So normally chlorine would be neutral on the periodic table. But if you see chlorine in the environment, it's usually negative. That's because it needs one more electron, so it steals an electron from somewhere else. It just takes it. And when it does, since it has more electrons than protons, it becomes negative, because electrons are negative, right? So it throws it out of balance. And that can happen to a gas. So imagine that these are the nuclei of a gas. Okay? Now normally, the electrons would be packed in pretty close, right? Like this, in shells. Now, some gases, when you apply energy to them, a lot of energy, you can actually cause these electrons to break free of the atom and float around the atom, like away from the atom. Free-flowing electrons. That's what plasma is. It's gas that's had enough energy put into it that all those electrons break free, and they're allowed to float around and do all sorts of crazy things. Y'all remember the cathode ray video we looked at? Where they had the glass tube and the purple light that was moving around with the magnet? It's been a while. Yeah. So that cathode ray, what happens is those electrons and the electrodes travel across the gap in that vacuum, and it creates light. The same thing can happen with plasma. If you had enough energy, all those electrons break free of their orbits, and they're allowed to move around. And when they do that, crazy things start happening. So now you got electrons just floating around out in the middle of nowhere. And that causes some really odd things to happen. Like this. That is plasma. What's happened here is some piece of metal has stretched across two high power lines, and when it made contact, it actually sent enough electricity through that it ionized the gas around it, like the air became plasma for a short period of time because of all that electricity. And that's what plasma looks like.
So plasma is fire?
Kind of. The fire is the burning of the oxygen you see around it. But see the color? That's the plasma. Right? So some of you all have probably seen one of these before. Hold on. That. Have y'all seen that before?
Isn't that the thing to make your hair go up?
Kind of. You can buy these at Spencer's. I've actually got one back there in the closet I'm going to break out during that lab I was telling you about. But that's a plasma ball. All it is a glass ball with an electrode. And inside the glass ball is gas. And when you turn it on, electricity goes from here to the outside. And it causes those electrons to create small connections. And it looks like electricity because it pretty much is. So that's charged gas inside that ball. That's why that works. And that's plasma. It's an ionized gas. And it is the highest energy level we're going to talk about. All right? It's the very top. So let's do a quick review. What is the lowest kinetic energy level? It is a solid. Good job. All right, what about the low kinetic energy level? Next level up. Liquid. Boom. Next up, high. Gas. And then finally the highest? Plasma. Just like that. Okay, good job, guys. Okay. Now, we are not going to talk about phase changes into plasma. I'll mention a word. It's on your assignment, but I am not going to test you over it. Okay? I just want you guys to know that beforehand. So we will test over phase changes into plasma. Exactly. Now I've got a couple of versions of this chart. All right. This is the easiest one to kind of see, but there's one on the back of your packet you're going to fill out by the end of this class. That's going to be the one we're going to use. Okay? Now, energy must be added to go from a solid to a liquid, because solid is the lowest and liquid is low. So you go up in energy, right? Right? So you have to get that energy from the environment. You have to add it to it. Energy is released when we go from a high energy to a lower energy. So if I go from a liquid to a solid, I have to release energy into the environment to do that. And I believe you've got a blank right there, don't you? Yeah. No, that's a solid line. No blanks there. All right, there's a couple of things on this one. It says right here, temperature is a measure of the average kinetic energy of the particles in a sample of matter. Particles. So whenever you take your temperature, you're not getting one reading. You're getting a bunch of readings that are averaged. So when that little piece from the thermometer touches the underside of your tongue, it's touching thousands, maybe millions of atoms. And it's getting an average reading of those potential, or those kinetic energies. And we average them out, and it becomes temperature. So temperature is a measure of average energy. Okay? The next thing we're going to talk about is the changes. To go from solid to liquid. Y'all know this one. What is that? What do we call it going from a solid to a liquid? Melting, right? Ice melts, right? Solid water melts into liquid water. So that's step number one. Right? As we increase the kinetic energy, we get several stages that we're going to go through, several phase changes. The first one, number one, right here, middle part of the page. Going in the low energy area, going from a solid to a liquid, we call that melting. The next one is in the middle energy levels. We go from liquid to gas. What do we call it? Vaporization. Now there's two kinds of vaporization. The first one is boiling, and the second one is evaporation. You guys have seen both of these, right? Your mom cooks macaroni and cheese, you get the pot of water and it boils. So where's the gas coming from when you boil something? Is it coming from the outside or inside? Right. Boiling is the vaporization inside a liquid. So you actually heat the liquid up enough that the gas escapes from the liquid. Now, what if I pour water on this counter? If I come back in a week, is the water going to be there? Yeah. No. Probably not. Why not? What do we call that erosion? Evaporation, right? So it evaporates. Evaporation is vaporization on the surface of a liquid, which is why water on a flat surface will evaporate quicker than water inside a cup, because you have less surface area. Okay. So those are all three of those. Next up, there is more. For instance, there are two key terms that we're going to talk about that you probably haven't seen yet. And that is heat of vaporization and heat of fusion. Now it says that the amount of heat required to cause a phase change, that is, change from solid to liquid or liquid to gas, that is heat of vaporization and heat of fusion. I have a different label for each. For instance, heat of vaporization is going from a liquid to a gas, or from a gas to a liquid. It goes both ways. If we go from a liquid to a gas, we're going from a lower to a higher state, right? So we have to add energy to move up. If we remove energy and we're fusing particles together, heat of fusion, going from liquid to a solid, we actually have to remove energy from that material to make it do that. Which is why if you take water and you put it in a super low energy freezer, you're pulling heat energy out of that substance. That's why it freezes. If I do the opposite, if I add to it, that ice becomes what? Water. Right. So heat of vaporization is liquid and gas. Heat of fusion is liquids and solids, going back and forth from either of those stages. Okay? Next up, last couple slides. This is a graph showing you heat and temperature for a substance. So on the bottom, we have the amount of heat energy we're adding. On the left, our y-axis, we have temperature. Now you would think that if I add heat, that temperature would rise steadily, right? More heat, more temperature. More heat, more temperature, right? But you'll notice these flat spots. You'll see these flat spots? Those flat spots are the heat of vaporization and the heat of fusion. Right here is the amount of energy. I'm still adding energy, but the temperature's not going up, right? That's because when I add that energy, a certain amount of it is required just to change from a solid to a liquid. So there's that short period we call heat of fusion where energy is added, but the temperature doesn't go up. It just changes from a solid to a liquid. Same thing happens when you go from a liquid to a gas. There's a period where you add heat, but you don't actually increase the temperature. All that energy added turns it from a liquid to a gas. And that's what heat of vaporization and heat of fusion are. It's the amount of heat required to cause a phase change. Y'all got that? Okay. This is the last bit. Back page right here. You're going to fill this out. I want you to add whether or not, or I want you to put on here whether or not you're going to add or release energy. So fill the blanks with the melting, boiling, freezing, condensing. And then I want you to guess. Are we adding or removing heat to cause that phase change? I'll show you at the end. Give you guys a little bit to fill that out. Y'all have seen this before, right? Something like it? No? When y'all learned about solids, liquids, and gases, you didn't learn about changes of state at all? I figured you should have. That's why I'm kind of covering it again. So I figured maybe it wasn't very fresh, right? Try to get you guys caught back up. Because you're going to see a lot of this stuff in chemistry. Get you guys ready for that. I remember taking chemistry in high school. I did not like it. Now it's one of my favorite subjects. It was hard in high school. I didn't like it. I didn't like things that were hard. Go figure, right? All right. Has everybody got their blanks filled in? Not yet? Just want to tell you guys, this is probably one of the best lessons I've had with you guys. Y'all have been attentive. I get you to answer a little more questions. Y'all awfully quiet. But I really appreciate y'all focusing and paying attention. I really do. Thank you so much. All right. Let's see if your guesses are correct. Do we add or remove? So, all of these up top are all adding because we're moving from a low state to a high state, right? All the ones on the bottom, we're releasing energy because we're going from a low state, a high state back to a low state. So we add energy to melt, and we add energy to boil, or we can add energy to go from solid to a gas. We call that sublimation. That's probably a new word for you guys, right? Did y'all learn about sublimation? No? You've heard about it. Sublimation is awesome. Have y'all seen dry ice before?
Yeah.
Y'all want to do some dry ice tricks in class? We're going to do that not next lesson, but the lesson after that. So, you're going to keep it, and I'm going to check it next class. And give you guys an opportunity to look over it, but I want you to practice keeping up with your materials. All right? We've got about 5 minutes left. So what I want you guys to do is get your vocab turned in, get your timelines turned in. If you need any of these, I'll get you some sheets. All right? Thank you guys.